Hello, greetings. So before we begin to talk about non-ideal solutions in Chapter 12, I first want to review properties of ideal solutions that we've already discussed before or discussed in Chapter 11. So first, remember the concept of an ideal solution is a solution in which all intermolecular interactions are exactly the same. So if I have a mixture of component 1 and 2, component 1 is just as comfortable in that mixture of component 1 and 2, or that 1-2 mixture, as it is in a system of just itself. So an ideal solution is a system in which all intermolecular interactions are exactly the same. And in the pure component limit, all solutions approach ideal behavior, right? So a solution of pure component 1 is an ideal solution, right? All the intermolecular interactions in that pure system are exactly the same. Okay, and so to kick off our discussion or review of properties of ideal solutions, first, okay, if we again let f be an arbitrary thermodynamic state function, okay, remember, okay, that f can be written as sum over I xi f by the molar average of the pure component f's plus delta f of mixing, okay, and in case I forget to mention it, right? Remember, when we talk about property changes upon mixing, right, if I think about mixing a beaker of pure component 1 with a beaker of pure component 2 to form a mixture of component 1 and 2, what I'm referring to is I have a mixture or a beaker of pure component 1 at a given temperature and pressure. I'm mixing it with a beaker of pure component 2 at the same temperature and pressure to form a mixture at the same temperature and pressure, right? So those pure beakers I'm mixing together, that final solution I form, right, those are all at the same temperature and pressure. So I'm mixing at constant T and P. So F here, this would be the molar F in my mixture is equal to the molar average of the molar Fs of those pure component systems I'm mixing together, okay, at the same T and P, plus delta F of mixing, right? And so to add functional dependencies, just to make this clear, okay, so remember F would be a function of temperature, pressure, and composition. Fi would be pure component F, so that would just be a function of T and P. And then delta F of mixing, okay, well, that's going to be a function of temperature, pressure, and composition. Okay, so F can be written as molar average of pure component F's plus delta F of mixing. The other relationship that we'll take advantage of, okay, is remember F can also be written as the molar average of the partial molar F's in my mixture. Okay, so F is F of my final mixture. F bar I would be the partial molar F in that mixture. Okay, both are a function of temperature, pressure, and composition. Okay. All right, so what we're going to first do is we're going to recall our expressions for delta F of mixing, for enthalpy, internal energy, volume, entropy, and molar Gibbs free energy of an ideal solution. Okay, so in an ideal solution, okay, remember in an ideal solution, all intermolecular interactions are exactly the same. Okay, so it follows that delta H of mixing is equal to 0, delta U of mixing is equal to 0, and delta V of mixing is equal to 0. Okay, cool. Okay, and as an aside, remember delta H of mixing, right, is going to be equal to delta U of mixing plus P delta V of mixing. Right? H is defined as being equal to U plus PV, right? And so I can write the equivalent expression for property changes upon mixing, where remember P is constant during that mixing process. Okay, so for an ideal solution, the enthalpy, internal energy, and molar volume upon mixing are all 0, right? And it should make sense, right? All of my intermolecular interactions are exactly the same. Okay, now I should ideally put a ID up here as well to designate these as ideal solutions, but just remember, we're just talking about ideal solutions here. Okay, now, okay, entropy of mixing. Okay, so when we talk about entropy of mixing, okay, remember I've stressed before, the key term to remember is sum over I, xi log xi. Okay, delta S of mixing. Okay, the key term to remember is sum over I, xi log xi. Now, delta S of mixing is always going to be greater than 0. It'll be equal to 0 in the pure component limits. Okay, but when I don't have a pure component system, delta S of mixing will always be, positive. So if I look at this, xi will always be less than 1, right, except in the pure component limit. So xi will always be less than 1. So log xi then will be negative. Okay, so in order for delta S of mixing to be positive, I need a negative sign. And it's going to be negative r, where r has the same units as entropy. So delta S of mixing is negative r sum over I xi log xi. Okay, then delta G of mixing. Okay, remember the key term to remember is sum over I xi log xi. Now delta G of mixing will always be less than or equal to 0, right? It'll be equal to 0 in those pure component limits, but delta G of mixing will be less than 0. So xi is less than 1, log xi will be negative. So I'll need a positive sign up front, right? It's going to be negative. Then I multiply by RT. RT has units of energy, right? The same units as G. Okay. And if you could just remember one or the other, remember just as we saw with H here, G is defined as H minus TS. So delta G of mixing is equal to delta H of mixing minus T delta S of mixing, right? Mixing is done at constant temperature and pressure. So delta H of mixing 0. So if I just remember one, then it can easily back out the other. Okay, cool. So these are our property changes upon mixing for an ideal solution, which you should remember, right? They are also the same as property changes upon mixing for an ideal gas. Okay, cool. So that would lead then for an ideal solution. Okay, remember F is equal to sum over I xi fi plus delta F of mixing. Okay, so that would tell me then that the enthalpy, again, we're only talking about ideal solutions, right? The enthalpy of an ideal solution would be equal to sum over I xi hi plus delta H of mixing, right, which is 0, right? So I'll just won't even bother to write it. Okay. U of my ideal solution. Okay, so if I were to put an ideal on here, U ideal, I've only got one superscript now, so be sum over I xi ui, and V ideal sum over I xi vi. Okay, so the enthalpy, internal energy, and molar volume of my ideal solution is just the molar average of those pure component values. Okay, cool. Okay, so ideal solution, all intermolecular interactions are exactly the same. Okay, now let's look at S. Okay, so the entropy of an ideal solution, okay, is equal to what? Well, it's going to be sum over I xi si, okay, plus delta S of mixing. Delta S of mixing is negative R sum over I xi log xi. Okay, G ideal, okay, the molar Gibbs free energy of my ideal solution is going to be sum over I xi gi plus RT sum over I xi log xi. Okay, cool. So we have our expressions for property changes upon mixing in an ideal solution. Okay, we have our expressions for enthalpy, entropy, internal energy, molar volume, and Gibbs free energy in an ideal solution. And now in the last part, let's get our expressions for partial molar properties in an ideal solution. Okay, and so what we leverage here, okay, is again F could also be written as sum over I xi f bar I. Okay, so these two expressions are equivalent and must be consistent with each other. Okay, so if I were to start with H ideal, okay, so H ideal, okay, is equal to sum over I xi hi. Okay, Okay, so that was our first expression here by plugging in delta F of mixing. That's going to be equal to, or equivalent to, sum over I, xi, h bar I. Okay, and we'll put a superscript ideal on there for our ideal solution. So it follows then that for these to be equivalent, my partial molar enthalpy of component I in an ideal solution is just equal to its pure component value at the same T and P. Okay, and to write my functional dependencies again, this would be a TP and XI, and HI is a function of T and P. Okay, and so you could do the same thing, and you would find, so that's enthalpy, okay, internal energy, my partial molar internal energy of component I in an ideal solution at TP and XI is just equal to its pure component value. And then same thing with my partial molar volume. Okay, where again, remember, an ideal solution is a system in which all intermolecular interactions are exactly the same. Okay, and so, when I think about a partial molar property, right, it's the effective value in solution. So if I think about molar volume, okay, the molar volume of pure component I in a system of pure component I, it's the average volume. Okay, and so when we talk about volume, remember there could be a hardcore volume, right, the space that molecule actually occupies, plus a buffer region, right, because there's going to be some void space between those interacting molecules, right? They're molecules in a force field. Okay, so the molar volume VI would correspond to, in that pure component system, the average volume, right, taken up, both that excluded volume and then that shell around it, that average volume per mole. So in an ideal solution, if all my intermolecular interactions are exactly the same, I'd expect that, well, the excluded volume will be the same, but I'll expect that buffer region around the molecule to be the same as well, since all those molecules are interacting in exactly the same way. All right, a 1-1 interaction is the same as a 2-2 interaction, is the same as a 1-2. Okay, cool. Now things change a little bit for S and G. Okay, and I put a ideal on there, right? So for entropy, okay, so the entropy of my ideal solution is sum over I, xi, Si, plus delta S of mixing, which is negative R, sum over I, xi, log xi. Okay, and we said that S ideal could equivalently be written as sum over I, xi, S bar ideal. All right, the molar average of the partial molar properties. Okay, so again, these two expressions must be consistent. Okay, so what I'm going to do is I'm first going to take this left-hand side and rewrite it. Okay, so first thing I'll do is, let's take it in baby steps. Okay, I'm going to take the first term, I'll write it as just sum over I, xi, Si as before. But now here, okay, so actually we'll bring R in as, or negative as well. R is just a constant, so I'm going to bring this negative R into the summation. I'm going to write it as sum over I, negative R, xi, log xi is equal to my sum over I, xi, S bar I ideal. Okay, and so now, and actually, let's even bring it in further, so make it more obvious when we collect terms here. Okay, I'm going to write this as negative I times negative R log xi. Okay, so it'll be a times there. Okay, because now I can collect terms, right, in terms of sum over I, xi. All right, this is sum over I, xi, Si minus R log xi is equal to sum over I, xi, S bar I ideal. Okay, so these two expressions are equivalent. Okay, and so for in order for that to be true, it must be the S bar I ideal, okay, which again is a function of Tp and Xi. All right, that's my partial molar entropy in my mixture, is equal to pure component value at the same T and P minus R log xi. Okay, cool. Okay, this term will be positive since xi will be less than 1. And so my partial molar entropy in my mixture is going to be greater than the entropy of my pure component state. Okay, cool. And I find this later expression pretty interesting as well, all right, because this is just my pure component system minus r log xi. And so when I think about an ideal solution in which all of my intermolecular interactions are exactly the same, so what causes my entropy of mixing to be positive, it's solely a combinatorial term. All right, so if I have a mixture of component 1 and 2, and they're interacting in exactly the same way, okay, that's great. But if I had, Superman's, X-ray vision, what would it, be X-ray vision? But if I could, superhero type vision, where I could actually look at my final solution and I could distinguish my 1 molecules from my 2 molecules. All right, so say one was red, one was green. Say they were different colors. So if they were distinguishable, so if I could actually see that, then what would happen is when I create a mixture, even though all these molecules interact in exactly the same way, they're distinguishable, so there becomes more unique configurations available to my system. All right, so if I were to take a red molecule and a green molecule and interchange them, change their positions, I've just created a completely new configuration. When I have a system of just pure component 1, I swap the position of 2, 1 molecules, nothing's changed, right? That new configuration's identical to the old one. Okay, and so that configurational change then, right, is accounted for in just this term, negative r log xi, right? Oh, cool. All right, and so then when it comes to g, we can get g a couple of different ways. Okay, let's do option number 1. Okay, way 1 would be, well, remember, g is defined as being h minus ts. Okay, so partial molar gi in an ideal solution is partial molar hi in an ideal solution minus t partial molar s in an ideal solution. Okay, so h bar I ideal is just hi, okay, minus t. Now I can plug in for s bar I ideal si minus r log xi. So factoring or expanding, g bar I ideal is equal to hi minus t si plus rt log xi. Okay, where hi minus t si, that's just equal to gi. So g bar I ideal, I can write as being equal to gi plus rt log xi. Cool. The other way I could get it is doing a similar matching exercise. So g ideal is equal to sum over I xi gi plus rt sum over I xi log xi, and it has to be equal to sum over I xi g bar I ideal. Okay, so playing with this first term, okay, r and t are constant, so I'm going to bring them into the sum. All right, this is sum over I xi gi plus sum over I xi, okay, times rt log xi is equal to sum over I xi g bar I ideal. Okay, collect terms and get sum over I xi gi plus rt log xi is equal to g bar I ideal. Oh, nope. Jumping at sum over I xi g bar I ideal. Okay, so matching, we get that g bar I ideal, okay, which again is a function of temperature, pressure, and composition, is equal to gi, my pure component value at the same T and P, plus RT log XI. Okay, beautiful. right, and so with that now, we've worked out our expressions for our partial molar quantities. Okay. So, we worked out that, h bar I ideal is equal to hi, u bar I ideal is equal to ui, v bar I ideal is equal to vi, s bar I ideal is equal to si minus r log xi, and g bar I ideal is equal to gi plus rt log xi. All right, so we worked out our expressions for our partial molar properties in an ideal solution. We worked out our expressions for our molar properties in our ideal solution here, and we worked out our property changes upon mixing for an ideal solution that we have here. All right, and so this was covered in chapter 11. Wanted to review it here because they'll come into play in chapter 12 now when we talk about non-ideal solutions. We're going to think about deviations from ideal behavior and work out those appropriate expressions.